Hello, welcome to our video on graphing polar equations. In this video, we're going to take a look at some techniques used to produce and analyze graphs of polar equations. Now, you probably have a polar grapher on your calculator, which is a great tool to have. However, for much of the work we're going to be doing in the future, particularly with polar areas, arc lengths, etc., it's important to understand the structure of the curve and how it is produced, things about intersection points, etc. And a lot of that will not be clear from just looking at the graph that is produced on your calculator. At the end of the last video in which we introduced polar coordinates, we saw a picture of the graph of r equals 1 minus cosine theta, the so-called cardioid, because it's heart-shaped. We're going to look at a few techniques for creating and analyzing graphs of equations of this sort. One fallback is always to plot points. Here we've made a table. Down the left column we have several values of theta running from 0 to 2 pi. And in the next column we've computed cosine theta, subtracted from 1 to get the r value. We can then plot these points, as we see here. And as we saw last time, what does it mean to plot a point in polar coordinates? Well, let's just look at an example. Theta equals 3 pi over 4. So we'll be interested in the direction 3 pi over 4. That angle right there. And then the answer of about 1.7, or 1 plus root 2 over 2, says we move along this ray until we get to that point, 1.7 distance away from the origin. And this is the point with coordinates roughly 1.7, comma 3 pi over 4. And once you've plotted enough points, you might feel you can fill in a smooth curve to get our picture something like this. Now, one thing you might want to notice about the cardioid shape we see here is that it is symmetric about the x-axis. In other words, the piece above the x-axis looks much like the piece below. What does it mean to be symmetric in this way? Well, if we have a point A on the graph, we've put that up here with coordinates r1, theta 1, then its reflection about the x-axis would be this point B down here. And we notice that in polar coordinates, B can be described by r1 comma minus theta 1. So if I draw the angle minus theta 1, which is in the opposite direction from theta 1, and go out the same distance r1 along this ray, we find we're at the point that is the reflection of A about the x-axis. We can predict this symmetry from the equation r equals 1 minus cosine theta. So if A equals r1 theta 1 is on the graph, that means we must have r1 equaling 1 minus cosine theta 1. So a graph is just a collection of the ordered pairs r comma theta that satisfy this given equation. Now cosine theta is an even function, so we also know that cosine of minus theta 1 equals cosine theta. So that tells us that r1 cosine theta 1 is on the graph if and only if r1 comma minus theta is on the graph. Because again, putting minus theta 1 in for theta 1 doesn't change the r value. And we see again from the picture up here that that corresponds to symmetry about the x-axis. So more generally, if we have a graph r equals f of theta, this graph is symmetric about the x-axis if f of theta equals f of minus theta for every theta in the domain of f. Sometimes polar equations are described implicitly, say in the form capital F of r comma theta equals 0. We dealt with implicit functions long ago in Calc 1. Again, the graph of the equation is the set of all polar pairs r theta that satisfy f of r theta equals 1. And the same principle holds here. If f of r theta is f of r minus theta for all theta values and r values, then the graph of f of r theta equals 0 will be symmetric about the x-axis. Now we're going to return to the graph of the cardioid r equals 1 minus cosine theta and take a look at another technique that can lead to its graph. So let's suppose we've already noted that the graph is symmetric about the x-axis. This means we can focus only on the portion of the graph above the x-axis, that is for theta from 0 to pi. Now here we're going to start not by looking at the polar graph, but by looking at the Cartesian graph of r equals 1 minus cosine theta. By that I mean we're going to go in the standard graphing plane and put a horizontal axis with the theta on it and a vertical axis with the r on it. And these take the places of y and x, and then we'll just go ahead and graph the r equals 1 minus cosine theta on this rectangular or Cartesian system. We're going to find this graph can give us some valuable insight into the structure of the polar graph, which we now see to the right. So here is the graph of the upper half of the cardioid, r equals 1 minus cosine theta for theta from 0 to pi. We've put in a couple colored lines here. The idea is that the vertical height on the left graph, the Cartesian graph, corresponds to distance from the origin on the right graph or the polar graph. For example, let's take a look at this point with theta equals pi over 4. You can check the height of that graph. The r value is 1 minus root 2 over 2. And over here on this graph, this tells us that if we make this angle of pi over 4 here and then move out along that ray, we have to go out this distance, this vertical distance, to get our point on the polar graph. Likewise, for the green segment here at 2 pi over 3, here's our angle of measure 2 pi over 3, and we've moved along this graph, turns out a distance 3/2 to get to that point. So what this shows us is that theta progresses from left to right along this horizontal axis, that the r value gets bigger. And that tells us then, as we let theta move us around from the x-axis to the negative x-axis, this counterclockwise direction, that again the r value gets larger. And you can see the points in the graph are getting further and further from the origin as we move around the curve. So this idea of looking at the Cartesian graph first and then understanding how r is increasing with the angle can give us some good insight into the structure of the graph. Now, before I continue on with graphing techniques, we should mention that there are other symmetries you might want to be aware of, in addition to symmetry about the x-axis. We also are going to try to be aware of symmetry about the y-axis and symmetry about the origin. And both of these can be identified by checking that the equation for the graph satisfies certain conditions. Now, a polar graph is symmetric about the y-axis. Let's see here. One way to check for that is if the point A equals r when theta 1 is on the graph, then this reflection about the y-axis is also on the graph. And you can check that this point can be described by r1 comma pi minus theta 1. So if the angle theta 1 is over here and I come theta 1 off the negative x-axis, then this angle will be pi minus theta 1. So this tells us putting in theta 1 and pi minus theta 1 should give us the same r values if we have symmetry about the y-axis. So this means if we have the graph r equals f of theta, and this is symmetric about the y-axis, then we can check that f of theta equals f of pi minus theta. Now, this is not the whole story because, as we saw in the last video, polar points have many names. So there are many, many different ways you can describe any point in the polar plane. And one thing we might notice here is that in this case, we have another way to describe this point. This is r comma pi minus theta 1, but another way to get to this point B is this. We could also put an angle of minus theta 1 down here, and then instead of moving in the direction of that ray, we move in the opposite direction. Remember, that tells us we have a negative r value, and so this point also has coordinates minus r1 minus theta 1. And symmetry about the y-axis might manifest itself in this way, so we actually have a couple different things we can check for symmetry about the y-axis. By the way, this graph is the polar graph of r equals sine theta minus 1/2 sine 2 theta. You might try punching that up on your calculator just to see how it works out and verify that this is indeed that graph. So in summary, we can check for symmetry about the y-axis by checking a couple things. If we have an r equals f of theta type equation and we have symmetry about the y-axis, we should check and see that f of theta is f of pi minus theta. That was our first instance. Or with the negative r connotation that f of minus theta equals minus f of theta. And again, sometimes the curve might be described by an equation given in implicit form, say f of r theta equals 0. And then the symmetry about the y-axis can be found by noting that f of r theta equals 0 if and only if f of r comma pi minus theta equals 0, or possibly that f of r theta equals 0 coincides with f of minus r minus theta equals 0. Again, these two characterizations, each reflecting different names of that symmetric point about the y-axis. Finally, symmetry about the origin can also be found by considering different names for points in polar coordinates. Now remember, symmetry about the origin says this, that if we have a point A on a graph, we then reflect that point about the origin, so we draw the ray to the origin, and then back out this direction the same distance, and that would be the point B that is symmetric about the origin from the point A. Again, looking for different names of points, we can characterize this point in a couple ways. One way to get from A to B is to go an extra unit pi around the circle, so add pi to theta 1. And if we again get this coordinate then, the same r value r1, but going with the angle pi plus theta 1, then we have the point symmetric about the origin. Another way to get that point is the following, though. We could also take a look at, again, just going in the direction theta, but then instead going back distance r1. So also we could have this point as being minus r1 comma theta 1. And sometimes we'll see that more than one r value can correspond to a theta value, and so we might get minus r1 for theta 1 as well as r1 for theta 1. That can especially happen in the implicit forms, and this is one of those forms. We don't just have r equals f of theta, but r squared and the theta are both tied up in functions there. So checking for symmetry about the origin, a couple ways to do that. We can check if f of theta equals f of theta plus pi. That was the first instance we looked at, but also considering other names for that symmetric point B. If our function is given as f of r theta equals 0 in implicit form, we can also check that f of r theta plus pi is also 0, or f of minus r theta is also 0. And again, both of those last two would indicate symmetry about the origin. Let's finish up with an example then, where we get to check for symmetry and look at our graphing techniques. We're going to analyze and graph the polar equation r equals cosine 2 theta. So we're first going to check for symmetry. So symmetry about the x-axis first. Cosine's an even function. So let's suppose we have a point r theta is on the graph, and that means that r equals cosine 2 theta. Now replace the theta by minus theta. We have cosine minus 2 theta is cosine of minus the quantity 2 theta. Cosine's even, so cosine minus theta is the same as cosine 2 theta, and again, that is equal to r. So this means if r theta is on the graph, so is r minus theta. So whatever graph we produce will be symmetric about the x-axis. Symmetry about the y-axis. Again, let's suppose we have a point r theta on the graph, which means that r equals cosine 2 theta. Let's replace the theta by pi minus theta. So there is cosine of twice pi minus theta, or cosine 2 pi minus 2 theta. Since cosine is periodic with period 2 pi, we can drop the cosine without changing the value of the function output. And again, the evenness gets us back to cosine 2 theta, which is r. So we know that r comma pi minus theta is also on the graph, so we also have symmetry about the y-axis. Now, it turns out if a graph is symmetric about both the x and y axis, it will also be symmetric about the origin. It's a good thing to know, but we're still going to check the origin symmetry using the criterion we developed for testing such symmetry earlier. So with symmetry about the origin, if r is on the graph, again, then r equals cosine 2 theta. So let's take a look at what happens if we add pi to the theta value. So if we look at cosine of 2 times the quantity theta plus pi, then we find this is cosine of 2 theta plus 2 pi. And again, the periodicity of the cosine makes this the same as cosine 2 theta, which is r. So that means r comma theta plus pi is also on the graph. And so this again proves the graph is symmetric about the origin. So let's produce the graph. Now, because we have symmetry about both axes, and as a consequence the origin too, we really only have to graph the part of the graph that corresponds to the first quadrant. That is, theta values running from 0 to pi over 2. So we're going to analyze that piece of the graph very carefully, and then using symmetry, complete the graph for theta from 0 to 2 pi. So in this picture, we've shown the graph of that should be r equals cosine 2 theta for theta from 0 to pi over 2. Again, we start with the Cartesian graph, r-axis vertically, theta-axis horizontally. And we've put some red lines on there indicating their heights, indicating r values at certain angles such as pi over 6, pi over 3, and even pi over 4. So when we look at the polar equation, or start to look at that, the colored segments have heights equal to the signed distances, that is plus or minus, along the rays at angles given on the horizontal axis. So for example, this point right here, theta equals pi over 6, is in orange, and that corresponds to this orange point and segment over here. We go at angle theta, go unit 1/2 along that distance to get the point 1/2 pi over 6. The red line over here, this vertical line, corresponds to the fact that when theta is 0, that is, we're moving along the positive x-axis direction, the r value is 1. And then one more, let's take a look at the green segment here, which is angle pi over 3, and that is shown right up here. This is the angle theta equals pi over 3. We see that for this value, the r turns out to be negative. We have something below the axis. When we graph a negative r in polar coordinates, we don't go in the direction of the angle, we go opposite, so we have to go back this direction, and that gets us to the point down here with coordinates minus 1/2, again r is negative, comma pi over 3. And then finally this point down here corresponds to the theta equals pi over 2 value, again negative, so even though we might come up here to pi over 2 in that direction, we go back in the opposite direction, distance 1, to plot the point down there. Okay, so let's then fill this in a little bit more appropriately. So what we see up here is the following. So in this picture, again, we see now that as theta runs from 0 to pi over 4, that's this red portion of the graph, the r value starts at 1 and drops down to 0 by the time we hit pi over 4. So I'm going to draw in this angle pi over 4 here, and what this piece of the graph, the red piece of the graph on the polar graph, what this graph shows is the r value decreasing as theta runs from 0 to pi over 4. Now, when we hit pi over 4, and go beyond that, we get the green part of the graph where r is negative. So even though we're looking at angles from pi over 4 to pi, which would be up here, the r negative value shoots us back into the opposite quadrant. And so if we continue this line here, what we would have thought might be up here actually turns down to be in the third quadrant down here and gives us that nice picture. So this is what I mean by drawing the Cartesian graph and then using it to kind of direct your drawing of the polar graph here. Again, looking at where the Cartesian graph hits 0 and at what values can guide us in helping us get the positive and negative r values right. Okay, so now that we've taken care of the 0 to pi over 2 part of the graph, we can start to impose the symmetry. So first, let's reflect this about the y-axis. So in that case, this red part here reflects to a red part in the second quadrant, and the green part reflects to give us a green part in the fourth quadrant. So that brings in the symmetry about the y-axis. And then if we take this picture reflected about the x-axis, we can see that we fill in these lobes, petals, and we find the final graph, which looks like a kind of neat-looking four-petaled flower. Okay, so what do we want to remember from this video? The graph of polar equation can be found in a couple ways. Certainly you can plot points, connect the points after plotted with a smooth curve. This is essentially the way your calculator plots polar graphs. Again, please make an effort not to rely too much on your polar grapher. Learn to analyze graphs by hand like we did here, because looking at the structure and flow of the graph, which you get by looking at the Cartesian equation, can be very valuable, very powerful tool. Secondly, you want to understand symmetry. This is very important. It can certainly cut down your work in graphing, but also give other insights in later applications. We looked at three types of symmetry. Symmetry about the x-axis. We can check that by knowing if r theta is on the graph, then r comma minus theta should be on the graph. And of course, these points have many names. You might also detect x-axis symmetry by noting that if r theta is on the graph, then so is minus r comma pi minus theta. You might check that when you plot these 2 points, they really come out to be the same. Symmetry about the y-axis can manifest in a couple ways also. If r theta is on the graph, then we would have r comma pi minus theta on the graph, and sometimes this will be manifested by noting that minus r minus theta is on the graph also. And again, we saw ways to check for that in the equations. And then also symmetry about the origin. If r theta is on the graph, so is minus r theta or r comma theta plus pi. And then finally, we found that drawing the Cartesian graph of r equals f of theta, so theta on a horizontal axis, r on the vertical axis, is a great way to get insight into how the graph forms, how it is structured as theta runs from 0 to whatever angle you want. You can follow the vertical height of the graph on the Cartesian graph, and that'll tell you how the distance from the origin varies as theta grows, and also when you might be going negative and having your graph be plotted backwards along some of the polar rays. So have fun with polar graphing. You can get some very, very interesting pictures with polar graphs. So we'll see you in the next video. Bye.